All right, let's start. Next speaker will be John Duchi from Stanford. Very nice to have John here, who has done a lot of work on optimization, and we'll learn more about optimization and robust optimization in particular.
Okay, great. All right. Save the applause until you're sure it's worth it. All right. We'll see. Yeah. I'm hoping this is more than some sort of strange vision quest where I sort of gesture vaguely at connections between fields. Anyway, I'm super excited to be here. So thanks for the invitation, Matus, and all the other organizers. All right. So I'm gonna, this is gonna be fast. It's gonna be kind of a blitz through. I'll post the slides, and I'm happy to answer questions more offline and as we go. We'll do our best. But I'm gonna try to sort of give this big picture overview of robust optimization from sort of the early 2000s to now, and at the same time try to start to make connections to kind of generalization and statistics. So that's a lot to pack into an hour and 15 minutes or whatever. We're going to do our best, and we'll see what happens. Okay, so I'm going to start with just sort of part one is just going to be robust optimization, and what does that mean? And the organization of, I flipped around the organization slide in part one. So organization, I'm going to spend the first bit talking about kind of classical robust optimization. I give a few examples of robust linear programming. That's going to be like from the early 2000s to the 2010s. We'll talk about chance-constrained optimization. And then at the end, we'll talk about what happens when we want to be robust to the sort of distribution underlying our data-generating mechanisms. All right, so let me start by motivating things by looking at just a standard linear programming problem. Okay, so this problem, the actual optimization problem we want to solve here is we're going to solve minimize C transpose X subject to AX is less than or equal to B. Okay, so this is actually, I don't know if is this too small for people to see? Yes. Okay. We'll try. I'm learning as we go. So we're going to try to solve the following problem. We're going to try to solve minimize C transpose X subject to AX is less or equal to B. And again, I will post these slides online, so if you feel like looking at them. So what's the game here? We're thinking of C as a vector of costs and profits. So this is classic optimization for two drugs. I have two drugs I want to manufacture. And then there are some constraints on their production. What do these constraints mean just in this particular example? These are 90 and 100. So think of X1 and X2 as the amount of kind of raw materials, like the actual chemical I'm putting into the drug. X3 and X4 are sort of how much, how much stuff I actually can produce. And so you can think of these constraints as saying 90 times X3 plus 100 times X4 is less than 2,000. Think of this as like some kind of storage cost. This is how much I can only store, say, 2,000 units of the drug. This is, say, some kind of labor cost. I can only have, 40 people or 50 people working on it, and I pay them less than $800, whatever. Okay, and this is some kind of, how much I collect some raw materials, and out of those raw materials, what fraction of the actual drug can I extract from those raw materials? Okay, so you can think of this as just some kind of production planning thing, and these are my profits when I sell the drugs to people, okay, or negative profits. So I want to minimize negative profits. I want to get as much money as possible. Okay, so this would be, if you were to take an optimization class, this is your first linear programming example. It's like, let's make lots of money selling drugs. I don't know, we're in Berkeley, so drugs of your choice. The dealers are getting more and more sophisticated. I don't know, go to People's Park. It's close by. See what they do. I have tenure. Doesn't matter. Also, this is academic. These are real questions, okay? Okay, but so now the real question is, all right, so we set up this optimization problem to maximize profits. And maximizing profits is a very Stanford thing, not a Berkeley thing. That's why we're That's what I have at Stanford. But so now the question is, what happens if in these constraints I just slightly change, the chemical composition of my incoming raw materials, and by tiny amounts, say like I vary this one by 0.5% relative error. So I change this 0.01 and I add or subtract 0.00005 of like my ability to actually extract things from this. Okay, and then maybe I change this one by 2%. Okay, and I just randomly perturb these things and I ask, okay, how much profits do I actually make when I do this perturbation? And the answer is that frequently I lose like 15 to 20% of the actual profits. So the amount of relative change on the kind of input, going back to this slide, was, the relative change was 0.5% or 2% relative change. And on the outputs, my actual profits went down, say, by 20% or 15% frequently. And so I just did a simulation here with this data. We regenerated a random constraint on how much raw materials I can actually extract. And we can see like, I don't know, about half the time I'm losing at least like 10% of the money I made, even though the input changes were sort of fractions of a percent. Okay, so the solutions we get from these problems are massively non-robust. And this kind of motivates the robust optimization perspective, which is rather than just solving this original linear programming problem to plan production or whatever you want to do, well, what we're going to do is we will instead consider solving the problem, minimize my losses or maximize my profits, but one second, Russ, subject to A plus delta at times X is less than B for all delta in some kind of uncertainty set, some sort of perturbations. Okay, sorry.
So when you said that you lose 15, 20%, is that recalculating the optimal solution every time for the adjustment, or trying to use the same?
Recalculating the optimal solution.
Okay.
Yeah.
So this formulation then will just like lower yourself by the 15-20% in advance, just making you less optimistic.
Actually, sorry. No, I apologize. Right. This is, I take my production plan, I modify the input slightly, I reuse the same production plan, and this is how much I lose. I misspoke in my answer. Thank you. Okay, so the alternative that we're going to take is, so rather than minimizing just C transpose X subject to AX less than B, we consider perturbations. And we say we want to be robust to these perturbations. And in this particular case, for this particular production planning example, okay, I'm going to allow the first entry of A. So that's the, how much stuff I can extract from my raw materials to vary by 0.0005. And similarly with the second entry of A. And all the rest of the perturbations are going to be 0. Okay, and then when we solve this, it turns out you can certify that the most you'll ever lose is 6% of your profits. Okay, so going back to this slide, you basically say, okay, as long as I'm willing to be robust, I can put this line right down the middle here, and I'm never going to lose anything more than this. Even if the sort of composition of my raw materials changes, I'm going to protect myself against this. So I come up with a certificate that I never do that badly. Okay. All right, so that's kind of the motivation for why we do these things. Any question on sort of the rough motivation here? Okay. All right, so let's talk more broadly. What is robust optimization? Okay, so the way we're going to formulate it is robust optimization. It's like convex optimization if you've taken that, but more robust. So we have a convex objective, which I'll always write as F0. This is my sort of objective function. Maps Rn to R. And then I have this uncertainty set script U. It's like the stuff I don't know, the stuff I'm uncertain about. And I have a bunch of constraint functions, Fi, which map our decision vectors, which are, say, Rn vectors or Rd or whatever, and vectors in this uncertainty set into the reals, where these are all going to be convex in their first argument. Okay, and then the general form is to say, okay, I'm going to minimize my objective, whatever it is, subject to the constraint that all of my constraint functions are less than 0 for all u in my uncertainty set, whatever that is. All right. Okay, so I want to so minimize my objective subject to my constraints holding for everything in my uncertainty set. So in the context of our robust LP, the uncertainty set in this case is just perturbations to the matrix, where the first entry is allowed to perturb by this much, and the second entry is allowed to perturb by this much. All right. Okay, and of course, this is equivalent to the optimization problem minimize f0, subject to the worst value of my function over my constraints being less than 0. And so this started in sort of the mid to late 1990s with problems in manufacturing design, and there's still active work going on now. And probably the names that we most associate with this are Aharon Bental, Dimitris Persimas, Laurent Elgaoui, who is sometimes here, Daniel Kuhn, Arkady Nemirovsky, and a few other people. So this has been kind of a big thing for the past like 20, 30 odd years. All right, so this is sort of the general form. And when we set up these, oh, sorry, let me just talk about how we actually set these problems up. Sort of a side comment. Yes, I'm sorry? We're going to get there. Where did I say it here? No, right here. Oh, I'm sorry. So you might have noticed that our function f0, I said, was always just a fixed function. There's no uncertainty in the objective function. And the reason for that is because I can always replace my function with, if I was uncertain about my objective, I just replace it with the worst value of my objective. And that just becomes a fixed function again. Or equivalently, I can rewrite this in what's called epigraph form, meaning I replace my objective with a scalar t and just say t has to be bigger than f0. And since I'm minimizing, I'm just always going to push t down to the bottom. All right, so we can always just assume that the objective is fixed. There's no uncertainty in the objective. There's only uncertainty in any of my constraints. Okay, so that's just a side thing. Also, if we had equality constraints, which you're familiar with from optimization, we never have uncertainty in those because that doesn't make any sense. Like if I told you, hey, I have linear equality, A transpose X plus some uncertainty is always equal to a constant. There aren't very many functions that satisfy that, right? There's one. It's called A is 0 and B is 0. Yeah? Okay. So other than that, so anyway, so equality constraints will never make any sense. We're only going to have inequalities. Those are the only things we're ever going to be uncertain about. Okay. So anytime you formulate robust optimization problems, you have to ask yourself 3 questions. 1, is the robust formulation useful? Like, is it actually addressing the problem you care about? 2, and this is a big one, can you actually compute this thing? Like, can I actually compute these suprema? These are very important questions and often very challenging. And the 3rd one, which is kind of be most of our focus today because we're sort of taking a more statistical perspective here, a machine learning perspective, is how do we choose this uncertainty set? Like, where is it coming from? Like, do you just pull it out of your hat? You're like, well, you know, I think that in my production problem, like my raw material composition might change by 5%. Where does that number come from? Like, it's sort of out of thin air. And so you have to have some care about how we choose these uncertainty sets. All right, and so I will say we're going to punt on this and just sort of assume that it's going to be useful. Is the robust formulation computable? This is a big question in all of robust optimization. And because we only have an hour together or so, I'm not going to spend a lot of time answering it, but briefly. So, and this will only really make sense if you're an expert in optimization. Duality is what comes up. And so often what we do is we try to take dual versions, Lagrangian duals of these problems to give ourselves kind of computationally tractable formulations of these things. And if that didn't make sense to you, sorry, Andre.
We're punting on one, but just like maybe since we're going to punt, are there versions of this machinery, for instance, where instead of your kind of prior over the perturbations being uniform, you have some like, actual distribution? Like maybe you think, you're not exactly sure how much like, the materials are going to deviate, but you're pretty sure like it's a kind of a Gaussian around.
Oh, absolutely, absolutely. And I think that actually is going to come down into this choice, is how we model uncertainty in our problems, or how we think about uncertainty or where it comes from. And that's going to be one of the big questions. And so this choice and justifications of this are frequently the important things. And often these will come from kind of probabilistic or other statistical considerations. And I'm going to write that in quotes. So sort of statistical considerations. All right. Yeah, sorry, Ryan.
It's a big question, so feel free not to spend time on it. But is there much interaction between robust optimization and variational analysis? Because they both look at some auxiliary parameter. Here it is. Mm-hmm. In variational analysis, I try to characterize how much X changes with you, the solution. Right. And if it didn't change much with you, then you'd think I probably wouldn't need to do anything robust, right?
Right.
So somehow the amount that the variational analysis would tell you somehow how much is changing which things.
Yeah, I'll give you two answers to this. One is I don't totally know. I don't believe there are sort of deep connections that anybody has made saying somehow they're equivalent. At the same time, yeah, if what robust optimization solutions should do is give you things that are sort of relatively stable to underlying perturbations. But that's a bit vague. So, okay. All right. So the sort of most common choice that we make in the kind of optimization literature or research literature for these uncertainty sets is to model them probabilistically. And so then the game is, or sort of the most frequent idea that you will see is, all right, so we have this uncertainty set U, it's a modeling choice. We're going to let U be some random variable with a distribution of some form or other. We make some assumption that U has a distribution. And then we want constraints of the form that the probability that I fail to satisfy my constraint is less than delta, where delta is some small number. You're willing to tolerate a delta probability of failing to satisfy a constraint, but you want that to be small. You know, if you were building a bridge, you say, okay, with probability 99.999%, the winds are going to be less than 200 kilometers an hour on the bridge. Okay, if the winds are more than 200 kilometers an hour, I'm willing to let the bridge be deformed, but otherwise the bridge has to be stable. Okay, because if your bridge had to be stable under like 1,000 kilometer an hour winds, you're going to use too much metal to build it, and that's going to be a mess, right? So now the challenge is that having an actual constraint like this is often hard. Typically, these give you these weird non-convex constraint sets, and they're hard to work with. It's really hard to work with things of the form 1. And so what we often do, and this is where robust optimization comes, is we find this uncertainty set U. We construct it via cleverness or magic or something like that, where with probability at least 1 minus delta, this random vector U, or this random variable, uncertainty random variable U, belongs to that set, potential uncertainty set with high probability. And then, of course, a sufficient condition for this probabilistic guarantee is that F is always less than or equal to 0 for all of my vectors in my constraint set. Okay? And this is sort of the logic, and this is where we start with, is we say, okay, here's some set where my random perturbation in my problem is going to be with extremely high probability. Let's just make sure I'm always satisfying my constraints for everything in that perturbation set. Okay, let me give a quick example here with Gaussian data, just to sort of give ourselves some idea of what's happening. All right, so let's again think of our linear programming problems. I want to minimize C transpose X, standard linear program, and then I'm going to have so usually what's the usual form of linear programming? I apologize. Usually we would write minimize C transpose X subject to AI transpose X is less or equal to BI for I equals 1 through, say, M, which is, of course, equivalent to the constraint that AX is element Y is less or equal to B, where A is an M by N matrix. Well, what we're going to do is we're going to allow these the rows of A, which is AIs, we're going to allow these to be perturbed with Gaussian noise. Okay? And we could allow BI to be perturbed with Gaussian noise. I don't really care. But let's just say that we're allowing A's to be perturbed by Gaussian noise. And then what we want to guarantee is that the probability that even, is this thing showing up? Yeah, okay. That the probability that even under these perturbations, so AIs are now random, that we exceed our kind of constraint is less than or equal to delta. All right. And what we're going to do is let these coefficient vectors AI are going to be normal with a mean A bar and some known covariance sigma. Okay. So if you just remember your sort of intro probability course, so AI transpose X, that's a linear function, a Gaussian vector. It's going to be normal. Its mean is going to be AI bar transpose X, and its variance is going to just be X transpose sigma X. Okay. Now, what would happen if delta was equal to, what would happen if delta was equal to 0.5? Well, so we know that what does a Gaussian distribution look like? It looks like it's symmetric. And so that would mean we just want to be to the left of 0, right? And so then you would just be left with the LP that AI bar transpose X is less or equal to BI.
So the conditions A1, A2, they could be dependent on each other. So the noise is independent.
Right. Right now we're just working with independent noise, and they could be dependent. Yes, absolutely. And more, the more sophisticated you can get in how you model the noise here, of course, the less conservative you're going to be in your solutions. You know, if you just model everything as sort of extremely noisy, your uncertainty set is going to get huge, and you're going to have to protect yourself against all sorts of deviations that might never happen. And you see this in practice. The more careful modeling you do, and I don't remember if I included examples in the slides later or not. I do in my lecture notes on this, but I don't know that I included them in the slides, so I apologize. So if you just had delta as 0.5 probability of failure, you just get the standard linear programming problem. Now let's ask ourselves, what happens if we had delta equals 0.1? You know, so now I want to fail less often. Okay, so then this is a more conservative constraint, and so this is going to say, okay, you actually have to be on the left of a larger line. You know, or if I'm allowed to fail with probability 0.9, like I don't care about failure, it's fine. This is almost like being anti-conservative. It's like, be risky, it's fine if you just fall off the cliff. Don't worry about it, right? And so just sort of graphically, this is what happens. Okay, so let's think about this. Let's think about the set of x's that satisfy that the probability that AI transpose x is bigger than bi is less than delta. Okay, well, since this is a Gaussian, you know, this is a Gaussian random variable, this is just the set of x's so that the mean minus bi, that's our scalar, minus the inverse Gaussian CDF times the square root of the variance. So this is, so phi is equal to the Gaussian CDF, or cumulative distribution function. You know, phi of t is equal to the probability that a normal, 0, 1 is less or equal to t. So this set is just the set of x's so that you satisfy this sort of linear plus norm type inequality. Okay, and so when delta equals 0.9, you get these weird constraint sets where you sort of kind of skirt inward almost, like you're allowed to fail with high probability. When delta is 0.5, you can see that our linear constraints, we just want to satisfy our linear constraints. And when delta equals 0.1, we become much more conservative. You know, to actually satisfy this constraint with probability 90%, the only set of x's that you're allowed to play are these. Does this picture make sense to folks? So this line right here, this is the line, this guy right here is the line x such that AI transpose x is equal to bi. This direction is the vector AI. And so as delta shrinks, meaning we're becoming more and more conservative, the set of available plays of x gets smaller and smaller and smaller. Yeah?
There's like ambiguity on how to define these things. There's not, these sets aren't, like that's not, I can find many sets where this is true.
That's correct.
And you've chosen to define, like, along each projection, I'm going to define a one-sided interval.
Yes.
Right? But I could have chosen anything.
You could, well, let me not, anything. Yes, you could choose anything that has a prescribed probability. So another.
Some way that's like, you could tell us like what you're looking for in general, or do I always think about one-sided intervals on projections or something?
Yeah, so Ryan's question is saying, you know, okay, so but if we look at this, right, you know, rather than this, what if you just said, okay, you know, A is equal to, you know, A bar plus just a bunch of independent normal, I'm just going to write it as identity, you know, a bunch of perturbations for the whole matrix, right? And so we could, instead of saying we have a row-wise perturbation of A, well, then this tells me something that, you know, A minus A bar in operator norm, say, is less than something like, this is an m by n matrix, so then this is going to be less than something like square root m plus square root n plus square root log 1 on delta with probability at least 1 minus delta. Is that right? Did I get the matrix concentration right? Who is Nikita here? Somebody who knows me. Yeah, he is. Did I get that right? Is that the right formula? Or did I mess up a dimension? Okay, good. Sometimes there's dimensions on this one. I always forget. What's that? No dimension on that one. Good. Okay, so we're happy. Great. Thank you. We have a little interactive session here. It's important. Right. So the point is, you know, this is a very different type of constraint than sort of an entry-wise constraint on these, and we could also use this instead. And sometimes that will give you looser constraint sets. Sometimes it will give you tighter. And so there is some modeling freedom in these things. There's no prescription for how you do it. The usual prescription is what things are computable efficiently that you can get a hold on. which is not maybe a satisfying answer. It's sort of like a vibes check. Okay. But this, so in this particular example, right, when we represent our constraints in this form, then the sort of robust optimization problem becomes minimize C transpose X subject to AI bar transpose X minus BI minus this phi inverse of delta square root of X transpose sigma X is less or equal to 0 for I equals 1 through M, right? And then this alternative form, which says that, okay, actually the entire operator norm of the matrix doesn't get perturbed by that much. That would give me this alternative robust optimization problem, which would be minimize C transpose X subject to A plus some perturbation delta times X is always entry-wise less or equal to B, where the operator norm of this entire matrix is less than some, say, epsilon, where epsilon is some number based on sort of the randomness properties in A. But this, I mean, and I'm being a bit vague here, but it's going to be, this is fairly easy to solve. This one is going to be a little more complicated. We're going to be left with a much more sophisticated optimization problem in this case, although this may give us tighter constraints that are easier, that are sort of less conservative.
I guess in general, with convexify, like if you end up with some set that's not convex or something, you would think it's convexal or something.
Yeah, I mean, this problem here is of course still a convex optimization problem because it's just a intersection of an infinite number of convex constraints, but sometimes these can be a little hard to work with. In this particular case, I mean, written like this is actually trivial because, excuse me, what are we going to have? You have that delta x, like, let me see if I get this right, the supremum over delta operator norm less than or equal to epsilon of, say, the ith coordinate of this is to just put all of the action on x itself. Right, so you make a rank 1 you make delta a rank 1 matrix in the direction of x, and so then this just becomes epsilon times x2 norm. So in this case, it's easy.
Just a semi-definite constraint.
Which is, but yeah, but I mean, it's just a semi-definite constraint like this, but we can imagine much more sophisticated cases, which does happen. Okay, so we say, okay, listen, anytime you have a robust optimization problem, which we have written here, it's always convex because we have convex objective, convex constraints. So should this be easy? Well, the issue is it's not always actually easy. So for example, let's suppose we were naive or something like that, and I said, okay, you know what? My uncertainty set U is equal to all vectors U in R to the n such that they belong to a box. U infinity is less than 1. Okay, so I have most of the time all my vectors are between -1 and 1. Well, if we had a quadratic constraint, which is a convex constraint, the issue is that to actually evaluate this constraint, the worst case over U requires a convex quadratic maximization in U. Solutions are always on the extreme points, and it's NP hard even to approximate this thing. Okay, so very quickly, if we're not careful, when we solve robust optimization problems, you run into these like NP hard things that are not good. And so this is one of the reasons why we have to be very careful when we design these problems. This is just to give you a sense of there are failure modes here if we're not careful. Okay, so the most common example that we run into in practice are going to be robust linear programming problems. All right, so again, this is minimize C transpose X, A plus U times X is entry-wise less than B. We always can represent these things constraint-wise. And the sort of simplest typical examples are things like, okay, suppose that U actually is this box constraint, so all of my U's lie in some delta width box. Well, then the supremum over U infinity less or equal to, say, delta of U transpose X is, of course, just delta times the L1 norm of X. And so the robust linear program is still just a linear programming problem because I have still linear constraints on X, or I can rewrite them as linear constraints, certainly. Right? This is equivalent to the constraint that A transpose X plus delta times the all ones vector times a vector, say, Y is less or equal to B, and Yi is greater than or equal to Xi, and Yi is greater than or equal to minus Xi. Okay? So I can always rewrite these things as linear programming problems. Okay? So there's no real huge penalty in terms of sophistication if we want to solve a lot of robust linear programs. Whenever our uncertainty set is polyhedral, can be represented as a linear program, we still have linear programming problems popping out. Let me give an example because I think this is kind of evocative of the type of things that we see. This is sort of fun, and it will get into understanding how we might actually represent uncertainty a little more carefully. Okay, so let's suppose we were going to solve a portfolio optimization problem. Okay, so here what do we have? And again, this is stylized. Don't try to start an investment company doing this. Or do, it's fine, but I'm not going to invest in it. So I have n assets that I might consider investing in, 1 through n, and there's some random multiplicative return Ri on each asset. Okay, and let's say I have known expected returns. So and these are mu I, where asset number 1 has the biggest mean return, and asset n has the smallest mean return, which is bigger than 1. Think of asset n as like putting your money in a savings account in the bank, which lets you get like 3% interest or whatever. Okay, then there's often what we call a certainty equivalent problem, meaning let's just assume that my returns are actually my expected returns. Okay, and if I just want to maximize my expected returns, subject to the constraint that I invest my full wealth, so x here is the proportion of my money that I put into each asset. So x transpose 1 is 1, so my proportions of wealth sum up to 1. I have non-negative wealth because I have $1 or something like that, right? And I maximize my expected returns. All right, so the solution to this, you just squint at it and think a little bit, and then obviously the right answer is to put all your money in the asset that has the best expected return. Gives me the most returns on average. Let's put all our money there. Bam, we're done. Okay. Now the issue is things with high expected returns typically are a little more volatile. They have higher variance, so sometimes that loses you money. So not a great idea. So the sort of robust optimization approach would be to say, okay, well, suppose that asset I's returns just vary in a range of mu I, that's my expected return, plus or minus some ui, where ui is some fixed value. Okay, and you would think of u1 because that's the maximum, the highest value, or the highest expected return asset as having the highest variance. So u1 is big, and un is say 0 because as I put it in the bank, I get 3% interest. It's FDIC insured. The end. Right, and then the robust optimization problem is maximize the sum of the infimum of all my perturbations. Like, what's the worst case thing that could happen if I put my money in this asset, subject to investing all of my wealth? Okay, and so then the equivalent problem there, just looking at what is this actual infimum value, well, each of my xi's is greater than or equal to 0, so this is equal to mu I minus ui times xi, right? The worst thing that could happen is that the asset just craters as much as it can, and this is the robust optimization equivalent of this. Okay, this is going to typically give you a very conservative solution, because what it's going to say is, you know what, put all your money in the bank because all the other assets could potentially lose money, right? So that's probably a little too strong. All right, so then you might ask yourself, well, what if we did something a little less conservative? Like we actually were trying to being a little bit careful, tried to use some of our probabilistic ideas to actually give ourselves an uncertainty set where most of the assets would be in there with reasonable probability. Okay, so now now this is a ridiculous assumption, but let's assume that my returns Ri are in between mu I minus ui and mu I plus mu I with mean mu I, and they're independent. Okay, so the returns are all independent of each other. So I have the ability to diversify investments across completely independent things. All right, so we're gonna, oopsie, excuse me. So this is the bonkers assumption. So the ridiculous assumption, but it's okay, we're just doing it. This is an example. These are independent. All right, okay, so then what I want to do is I want to maximize my returns. I'll call that as t is my expected return, or my actual return. I want to maximize this return subject to the probability that the returns are at least t is at least 1 minus delta. Okay, so my probability of getting less than t as my returns is at most delta. Okay, this is called the value at risk sometimes in investments or optimization. It's how much money do I get at the risk delta of losing, okay, losing all my money. Okay, and what we're going to do is rather than use this directly, because this could be hard to compute with, we just approximate this set with high probability bounds so that we can certify. So again, what is the game? It is to find a set such that, a set such that the sum of Ri xi bigger than or equal to t, that R such that this holds, has probability at least 1 minus delta, and then we use that. Okay, so if we can find a set where all of my returns are in that set with extremely high probability, then we optimize over the worst case in that set. That's going to be good enough, and that'll give us a less conservative approach than this sort of super robust, extremely conservative approach of each asset is as bad as possible. Okay, and then once we do this, how can we do this? Well, the simplest way is via Hoeffding's inequality or your standard kind of Gaussian concentration results, which probably most of you are familiar with. That, okay, if these returns are all independent, so again, these are assumed to be independent returns, then the probability that the sum of the returns minus their means times xi deviates by more than t. This is less than the e to the negative t squared over the sum of xi squared ui squared, where this is, again, remember, this is the maximum deviation that each asset can take. Okay, and so writing this a little bit differently, what do we do? Excuse me. I just map t goes to t times the square root of the sum of ui squared xi squared, so that this term becomes just t squared over 2. That's this. And then my deviation here is this. So then the probability that the sum of my returns, remember this is what I actually, my actual random return, the probability that this is less than my expected return minus whatever this deviation is less than e to the negative t squared over 2. Okay, so we want this to be small. Well, you just set t equals square root 2 log 1 on delta, where that's our desired kind of failure probability. And now I know that this is my sort of high probability, return. Okay, and that, of course, is just equal to, in this case, mu transpose x, that's my mean return, minus this penalty deviation of the L2 norm, that's the sum of the square roots, the sum of the squares of this quantity, and then the square rooted. Right, this is just equals square root sum I ui squared xi squared. Okay, so I got an alternative problem, which is instead of maximizing my average return, I maximize my average return minus a penalty for risk. Okay, and so this is kind of the riskiness penalty of my investments. So the larger my uncertainty is in a given return, the more penalization I have. But I'm willing to kind of diversify a little bit. I can suffer some risk, and we can actually do some simulations here. And so here I actually coded this up just for giggles. So here's my data. My mean returns are going to be 5% return plus 3 times n minus I over 10 times n. So that is to say, like if n is 1, that's I is 1, my best return, and I'm getting 1.05 plus about 3 over 10. So like 35% returns on my riskiest asset on average, okay? But it could collapse, okay? All the way down to the bank where I equals n, so I'm getting exactly 5% returns by sticking my money in the bank and doing nothing. All right, so nominally, if you are super risky, you're like, let's put all our money in the first thing. Like, you know, we're taking this thing to the moon, right? You got on Reddit, you got on Wall Street Bets, and bam, okay? I don't know what words they use there. But anyway, so that's what you did, right? And then if you were my mother, you were like, you know what? I love the bank. Let's just put all my money in the bank. You put everything here, okay? And then, you know, if you were a sophisticated optimizer like we all are, okay, you solve the, in this case, it turns out this is a second order cone problem. You linear term and then a quadratic-ish term. And that gives you this minimizer we'll just call x delta. It does not have a closed form in this case. Okay, and we're going to take our risk to be 10 to the negative 4 times 2. There's no particular reason for that. And you can actually run this simulation. And so we did this 10,000 times where I just picked random returns according to this distribution. And you can see what happens with the nominal investment, which is just put all your money in GameStop. Okay, yeah, okay. That sometimes you lose a lot. Okay, like you lose 30% of your wealth. Sometimes you gain a lot, and it's kind of evenly distributed all over the place, right? Now, if you're a conservative, you get literally every single simulation, you get exactly a 5% return. Okay, and with this kind of SOCP thing where I said, listen, I'm willing to tolerate failure probabilities, but they should be small, like 10 to the minus 4. Then we get this kind of bump around. On average, we get something like 20% returns with a few deviations to the left and the right. But so we're less conservative than this, more conservative than they just put all our money, ride that rocket ship to the moon, but we don't lose things very frequently. Okay, so this is kind of so this is the type of behavior we typically see. All right. Okay, so any questions on that? That was robust optimization in 25 minutes, which is ludicrous, but we did it. Yes.
Is that natural?
No. Oh, well, natural, sure. Of course it's natural because I'm, a professor and we give lectures and then you get to pretend it makes sense. That's what you would choose if you were to give a lecture on this and try to teach people. If you were actually at an investment firm, absolutely not. No, there's tons of correlation between the assets, and you would definitely try to model that. You would say, okay, Coca-Cola and Pepsi, right? Their returns are.
Even independently, wouldn't normal distribution be better?
I mean, normal is kind of weird because you could have a negative value, which in terms of the proportion of your wealth doesn't make any sense unless you're if you're allowed to short stocks, then you can have real issues there. So there, yeah, the real game, you model correlations between your assets, you're allowed to short things, you can take out options. I mean, there's way more sophisticated strategies. But really, I mean, it is the following statement is accurate, that you model your returns, you try to do some very sophisticated stuff to get the best estimate you can of, okay, the returns should be in this region with some reasonably high probability. Let's make our investments kind of, while we try to mitigate risk in case, so long as the returns are somewhere in this region where I'm pretty sure they're going to be tomorrow. Okay. But yeah, the assumptions and modeling we've done are sort of ludicrous. They're an object lesson to sort of show roughly what we do. Any other questions? Okay, great. Yeah, so big picture, what have we done? We said we wanted to solve robust problems. The big challenge is how do we choose the uncertainty set? And a natural way to do this is to model things as random and say, okay, I want to fail with only a prescribed probability at worst. All right, but there's, of course, a lot of wiggle room in how we decide this. Now, assuming we're okay with this, I'd like to jump into part 2, which is going to be called chance-constrained optimization, where we really dig into this probabilistic modeling here. Okay, so remember that, excuse me, when we're solving optimization problems, a big part of the game is that we want to certify that our solutions have certain properties. And so, excuse me, writing a chance-constrained optimization problem, which is related to the robust problems, I want to minimize my objective. I'm always going to be minimizing, but I want to have the constraint that the probability that I fail to satisfy one of my constraints is at most delta. So this is going to be called the chance-constrained problem. And we saw that we used these to justify robust optimization. But now the question is, okay, how do I actually deal with this constraint? Because typically these kinds of constraints would be non-convex. You can't necessarily represent them very well. So this is typically some kind of a non-convex. Often it's hard to work with, hard to deal with kind of constraint. Blah, 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 blah. So we don't. So we need to do something else. And the technique we're going to use is basically what's called a safe approximation to the chance constraint. And to do that, what we want to do is we're going to try to construct some kind of convex function where if this function gi is less than 0, then my constraint is satisfied. Okay, that's called a safe approximation to this function. All right, because what this says is that so long as I can satisfy this, then definitely all of my probabilities satisfy what I want them to apply. So this is a safe thing. It's conservative. We want to be conservative because we want to have certificates. We want to certify my bridge is not going to fail unless something really, really weird happens. Okay? All right, so how do we do this? All right, let's punt on this. I don't know why I put that there. Okay, so here's how we do this. Here's how this works. This is kind of a beautiful technique. So here's our trivial observation. So if phi is any non-decreasing function, with phi of 0 equals 0, then it's always bigger than the indicator that some value z is bigger than 0. So let's write this. Let's draw the picture, okay? This is a very sophisticated picture. Okay, this is the indicator function. So this is z equals 0 here. This is the indicator function that z is bigger or equal to 0. Okay? Now, if you give me any function phi, which is non-negative and increasing, or at least non-decreasing, and at 0 is equal to 1, or bigger than 1, then my function phi has to be bigger than that indicator. Yeah, everybody agree with that? The function that's bigger than the indicator is bigger than the indicator. Tautologies with John. Okay, so this is my function phi. Okay. Now the consequence for this is that for any scalar lambda, which is positive, the probability that z, a random variable, is bigger than 0. So think of this as failing to satisfy my constraint. This is less than the expectation of phi times 1 over lambda times z. Okay, what's going on here? This, of course, is equal to the expectation of the indicator that z is greater or equal to 0, right? But phi, we already literally said that phi has to be bigger than this indicator, right? Which is, of course, also equal to the indicator expectation of the indicator that 1 on lambda, because lambda is bigger than 0, is greater than 0, which is then less than or equal to expectation of phi of 1 on lambda z. Okay, and we'll see why I divided by lambda in a second. The reason for that will become apparent later, but just give me a free parameter. Basically, for any lambda here, this always dominates this. No problem, okay? And so in particular, if I have if I have this, that expectation of phi of z on lambda is less than delta, then definitely the probability that z fails to be less than 0 is less than delta. So this, if phi, so right here, if phi is convex, this is a sort of a safe relaxation of the constraint that probability that z is greater or equal to 0 is less or equal to delta. Right? Because now I have a convex function where if this thing is less than delta, then this thing is less than delta. This is a safe approximation to this. Okay, now the question is, how do we choose the best possible kind of convex approximation to this indicator function? Right, so what we're going to do is we gave ourselves this free parameter lambda right here. Well, we'll just choose the best one. Okay, so we knew that E of phi of z on lambda less or equal to delta. This implies that the probability that z fails is less than delta. Well, I can just multiply by lambda on both sides, lambda times lambda. Okay, and so whenever, so the best constraint says that if this holds for any positive lambda, some positive lambda, this is satisfied, then this holds. Okay, so we just try to take the best lambda for this, and you're like, well, gosh, Sean, this is kind of a mess. But if who here has taken a convex optimization class? Like 3 of you? All of you. Okay, great. What's the name of this function? There you go. Yeah, so this is the perspective transform of my function. And perspective transforms are always convex. That's right. Thank you. Yeah. That was very good. Thank you. Right. So we maintain convexity here. And as long as phi is an increasing convex function, so phi looks like this or something like that, then this is this now is going to be jointly convex in lambda and in x. So we have a jointly convex function. We've maintained convexity in our thing. And so this is the perspective transform. Excuse me, of phi, and then we composed that with a function f. Okay, and so this maintains convexity. This maintains joint convexity. As long as f is convex, then this function is jointly convex in lambda and x. Okay, and so in particular, I can choose the best possible lambda here, and I get that, excuse me, if the expectation of f of x, you run through this phi function, whatever it is, I don't care, it's any increasing function bigger than 0, or bigger than 1 at 0. If this is less than 0, this implies exactly that the probability that f of x fails to satisfy its constraint is less than delta. Okay. All right, so this was kind of an involved set of steps we've done. Yeah, question?
Your assumption is phi is increasing and convex.
My assumption is that phi is non-decreasing convex. So phi is non-decreasing. It's convex because we need to have it be, excuse me, we need to have it actually be a convex optimization problem. Otherwise, life is hard. And phi of 0 is greater than or equal to 1. So it's bigger than the indicator function. So we need to have something that looks like this. Okay. Now the question is, so this was kind of involved, and there's a lot of freedom here so far, but is there a best possible phi function to choose? Can anybody tell me? What's the best possible phi function? Turns out there is one. There's only one. What's that? No, but that's a good guess. That one's convenient for analytic reasons, but it's not the best. There's one that's literally the best. It's smaller than every other convex function you could have chosen, yes. So it gives you the sharpest possible constraint, yeah. Very, very close. Needs to be non-negative though, so. What's that? Daniel draw. Okay, so Daniel's drawing it with his hands. Yeah, exactly. So the best possible choice is what's called is the hinge function. Okay, so here's the function we want to approximate, which is just the indicator that z is non-negative, and all we're going to do is take functions of the form that are 0 on the left, and then they bounce up to the right. Right? And why is that? Why is that always the best? So give me any convex function. I'm gonna see if I can. Can I do this? Okay, I'm erasing too much, but that's okay. All right, so here's my indicator function. And now Ryan comes over and he's like, John, I have the greatest convex function. It is, it looks like this, okay? And he's like, this is the best one that we could possibly have. And well, okay, no, I'm sorry, Ryan. I can always sneak something below that and still above the indicator function, which is just, I can make a linear, oops, good. I just make this, am I gonna get to draw here? I just make this linear function here, and then when it hits 0, it just stops. Okay, so no matter what convex function you chose, I can always have a function of the form, like the 1 plus or 1 plus z positive part. Okay, that's going to be the smallest possible convex function I can get in there. Yeah. Yeah, so that's a great question. And that was, we've done this kind of magic here, where what I did is I multiplied and divided by lambda. And so then we just choose the lambda that makes this whole thing the smallest. And that's going to be the smallest. That's going to be exactly where we put the hinge function. Okay, so that was why we did this perspective transform, because that's what that gives me is when I choose this to be this positive part function here, this is going to be lambda times the expectation of the positive part of 1 plus, excuse me, z over lambda, which is, of course, equal to the expectation of lambda plus z positive part. Okay, and then when you take the smallest possible lambda there, you want this thing to be less than 0. This is going to give you exactly this quantity. And so that says what's the best place to choose the hinge to still certify kind of that I won't have a failure event. All right, and what you can see is that, and then we observe that if this quantity is less or equal to 0, then the probability that z is bigger than 0 is always less or equal to delta, because we're still making all of our safe convex approximations. Okay, and then just real quick, this particular function, it's so special it gets a particular name, which is called the conditional value at risk. All right, so if you've done a lot of investment for whatever reason, then you've seen this function before. But what is this function? Is we actually just divide out lambda. So let's do it. Let's do a quick calculation. What's the value lambda that's going to minimize this? So taking d over d lambda of this thing, I get that this is equal to expectation that the indicator that lambda plus z is greater or equal to 0 minus delta equals to 0. Or what do I choose lambda to be in this case? It's going to be one of the quantiles, right? So I just choose lambda. Can anybody tell me which quantile it is? Is it the 1 minus delta quantile? I always get these confused. Ryan, you're the quantile guy. Delta, 1. Yeah, just because I wrote it on the slide doesn't mean it's correct. That's you have a lot of faith in me. Anyway, I think that this says, so this is the probability that z is bigger than, or let's see, the probability that lambda is bigger than or equal to minus z is equal to delta, which is the same as the probability that z is bigger than or equal to minus lambda is equal to delta, or 1 minus, I mean, whatever. It's probably the 1 minus delta quantile. Yeah, maybe. Wait, which one? This guy? This is correct. This, whatever I'm doing up here is probably screwing us up. Lambda is equal to the negative 1 minus delta quantile of z.
Yes.
Sure, okay. Lambda equals to the negative 1 minus alpha, 1 minus delta quantile of z. Seems plausible. Okay, and I apologize. I should be able to do this on the fly. We could work it out together. One of you guys probably did. Okay, but excuse me. If you just divide this through by delta, again, we're only caring whether this is less than 0 or not, doesn't matter, then this particular quantity is called the conditional value at risk of z. So we say, okay, the conditional value at risk delta of z is just the expectation of z conditional on z being at least as large as its 1 minus delta quantile. Okay, and so this is somehow the best approximation to your chance constraints. So this is the best possible convex approximation to the constraint that the probability that z is greater or equal to 0 is less than or equal to delta. And we see that conditional value at risk of z delta being less or equal to 0 implies that the probability that z is greater or equal to 0 is less or equal to delta. And so in the context of optimization, if we actually had an uncertain optimization problem, this is the same as saying that the conditional value at risk of whatever my constraint is, f of x with my uncertain random variable u, this at delta being less than 0 implies that the probability that I fail to satisfy my constraint is less than or equal to delta. All right, and so this quantity is this sort of centrally important thing in the whole theory and development and practice of chance constraints and robust optimization. You make sure that whatever your random constraint function is, its conditional value at risk delta is less than 0, and that guarantees that the probability you fail to satisfy your constraint is less than delta. And that is a convex version of that constraint. Okay. How am I doing on time, Misha? I don't remember exactly when I'm stopping. I have 15 minutes? Okay, great. All right, so let's revisit our portfolio optimization problem. Let's take these two different approaches. We have, again, a random returns exactly as before. We're going to compare this conditional value at risk approach to this analytic approach that we chose, which was to literally model things as according to their kind of sub-Gaussian perturbations. Okay, and the way we actually evaluated this conditional value at risk is we just drew a bunch of Monte Carlo samples and said, okay, let's satisfy this constraint. And when you do this, this is me just plotting a histogram of the returns that we get. The average return for the analytic solution is something like 5%. I think I slightly changed the problem data, so 3% was your certainty equivalent. And the sort of guaranteed return according to your conditional value at risk was a little bit higher. So instead of like 1.45 or 4.5%, you were getting like 5.5% returns. Right, and you can see it's slightly shifted to the right. We get better returns slightly more frequently because this is a less conservative constraint. We are more accurately approximating the probability of failures. Ryan?
The property that one function dominates another in order to imply that their expectations are ordered.
Yeah.
But that's like potentially very loose.
Yes.
So is there some other way to get the property that you want by constructing functions that have the right expectations but not quite right?
Almost certainly. So for any given problem, there are likely to be more sophisticated modeling tools you could use to kind of do exactly what you want. But in terms of the general purpose thing, this is sort of the best thing we know how to do, or at least that I know how to do, is to do these kind of somewhat gross approximations.
I guess partly because it's like agnostic to the distribution of these.
Yes.
But what you're saying is if you told me a little bit more, I could help with this better.
Yeah, if you told me a little bit more, potentially I could do something better. I mean, with for example, if I actually had Gaussian data and I knew that, then of course, you know, Gaussian approximations are exact. But you know, but again, all of this, I mean, remember that these at some level are going to always be a little bit conservative, because at the end of the day, you know, we're really targeting certificates. We want to certify that with a prescribed probability, nothing bad happens. So there's no kind of average case. It's always these worst case things that we're sort of dealing with because we're doing this robust optimization approaches. Okay. All right. So in the last bit of the talk, which I'm going to blitz through a little bit, I'd like to talk at least a little bit about distributionally robust optimization, which is what's happened in the last 5 to 10 years as we've tried to make connections between robust optimization and kind of statistical machine learning and things like this. So putting on our sort of stat ML hats, we have a loss function, L, which maps parameters theta across some observed data into the reals. We want to minimize some expected loss, okay, under a true distribution P true. Okay, so this is the truth. It's wherever this is generating the data. That is to say, the average, you know, average loss according to this distribution P true. But of course, you know, you're only given a sample Z1 through N. Draw an IID from P true. And so the question is, what do we do? And putting on your kind of robusty optimization-y hat, as it were, your idea is that the empirical distribution, I plunk a point mass down at each one of these ZIs. This should be somehow near, and near is in quotes on purpose, the true distribution. Okay, these should approximate one another. And of course, you know, Nadi has told us this happens in statistical learning theory in very particular ways using VC dimension. At least I'm imagining he did. He did, yeah? Did you mention VC dimension? He did. Okay, good. See? I'm not as dumb as I look. I might be. But you know, so this should be near P true. And now the question is, what would, you know, if we were to put on our robust optimization hats, what would that mean? Well, what that means is what we should do, roughly, is construct some kind of confidence region, which I will write as script Pn, based on this empirical sample, so that one of the following two things happens. Either the actual true distribution belongs to this uncertainty set with a given probability 1 minus delta, because then we can use our tools from robust optimization that we've sort of at least hinted at to solve the problem. Or, you know, approximately we guarantee that, okay, with this confidence region, the actual true expected loss of my decision, of my model that I've fit, or whatever you're calling this, is less than the worst case loss over any distribution in this kind of uncertainty set that we've constructed. So if we can have one of these two things happen, then we can kind of apply the tools that we've developed and solve these problems. And this is the idea of distributionally robust optimization, is to try to tackle one of these two quantities, okay? All right, so this is kind of my uncertainty set. This is the analog of script U that we saw earlier. So this is my new uncertainty set script U, except now I'm just uncertain about the actual underlying distribution of the data. Okay, is that, at least Jibe, that connection seems fairly clear to folks? Okay, great. So assuming we have that, so what we'd love to say, you know, one version of this is we want to construct some confidence set so that the probability that the true distribution actually belongs to this confidence set goes to 1 minus delta. Okay, so many choices of this are possible. Unfortunately, many of them lead to intractability. And this, I will say that, like, this is still an active area of research. So active research here is figuring out how to actually do this the right way to actually solve these problems, okay? And I'm happy to talk more about that. We won't have time to get into the open questions, I think. But, you know, so here's some sort of a trivial example of how you might do this. Suppose we had real valued ZIs, observations, okay? And their variance was finite, all right? So then the central limit theorem, which we're hopefully all familiar with, it tells us that, okay, well, if I multiply by root n, then my sample mean minus the true mean, normalized by my, say, sample standard deviation, or my square root of my sample variance, that's approximately normal 0, 1 distributed, right? That's what the central limit theorem says, that this is supposed to have a normal distribution, no matter what your underlying thing is. Okay, so then we could say the set script Pn, that is the set of all possible distributions, whose means are within the sample mean, kind of normalized by my sample standard deviation and root n times z1 minus alpha. So here that notation means that this is the, oops, sorry, that should be a delta, by the way. This is the 1 minus delta quantile of a standard normal of normal 0, 1. So distribution satisfying this, and their actual true variance is less than, say, sigma hat squared plus a little error term. Okay, then the true distribution should belong to that set. Everybody agree with that? That's what the central limit theorem tells us, is that should happen. Now the issue here, and I'm not going to give explicit examples, is this is huge. This is like just this is a massive set of distributions. It's way too large to actually do anything useful. And for basically any interesting problem, if you were to try to compute this, say, supremum over here, it would just be plus infinity. And you're like, great, upper bound on my performance is my losses are less than infinity. Okay, that's not super useful, unfortunately. Okay, so we need to do something else. And again, this is why this is an active research area, is because a lot of the normal ideas you would have end up kind of breaking down a little bit. And so nailing down exactly how to construct these things is super important. You know, one common place, and again, I'm sorry, I'm going to blitz a little bit because of our limited time, is if your true distribution is supported on only, say, like k different items. Okay, so then the probability that x is equal to I is some fixed value pi, where I is one of our 1 through k. Then there are sort of standard results. Well, they tell us that the empirical mean minus the true mean is about normally distributed with the covariance of one of my random observations, which is the diagonal of p minus pp transpose. Okay, when we kind of renormalize this, you sort of studentize it or standardize it or something, well then the approximate distribution of n times p hat minus p interproductive with itself with a little correction here, it's something like a chi-squared distribution with k minus 1 degrees of freedom. That is to say, it behaves as the sum of k minus 1 standard Gaussians squared, which you should get that from this, or at least you can get that from this. Okay, so this is called the chi-squared distribution with k minus 1 degrees of freedom. But the point is, it looks like this. Okay, and I know what the sum of a bunch of independent Gaussian squareds, I know what their distribution is, and now this gives me a very natural uncertainty set in this case, which is I compute the 1 minus delta quantile of this, and now I know that's what this quantity is right there. Once I get that, I know that the true distribution, p, belongs to the set of things where the sum of p hat minus pj squared over pj is less than whatever this quantity is. Okay, and so that gives me a natural robustness set in this very particular case where I have a finite support. Okay, so this is like one example where we can actually solve this problem. Okay, I was going to talk about general phi divergences, but that's going to be a little bit brutal. So let's punt on that one. The other approach that has kind of blown up in the past like 5 to 10 years is what's called Wasserstein uncertainty sets, or optimal transport-based uncertainty sets. So what are these? So what these say is that if you give me a cost function that measures the cost of moving stuff from one point to another, so I have an underlying space z, I have a cost that measures how much, what does it cost to move z1 to some other z prime. The Wasserstein distance between these, or the optimal transport distance, is equal to this infimum. And what is this? What is this writing out? This is the set. So pi of pq is equal to all joint distributions such that, excuse me, pi of whatever, a, and then the entire space is equal to p of a. So I'm coupling these two distributions, and pi of the entire space with b is equal to q of b. Okay, so in pictures, what this is saying is figure out how to, you know, what I'm looking for is a joint distribution. I have an initial data distribution, say p. I have an alternative distribution, say q, and I want to ask, what is it going to take to move p to q? Like, what's the best way to move all of the stuff from p into the distribution q? Okay, so this is called the Wasserstein distance, and there's a ton of work on these, lots of beautiful things. But we have these convergence guarantees that if you have d-dimensional vectors and you use just the L2 distance between z and z prime as your cost, so, you know, literal Euclidean distance from one to the other, then the Wasserstein distance between your sampled empirical distribution and the true distribution looks like something like n to the negative 1 over d, which at least goes to 0 as n goes to infinity, sort of, for some values of d. Okay, and you know, you should think of this as, you know, if I have my true distribution floating around here, I get a bunch of point masses, more of them are in the middle, and fewer of them are out in the tails. And then I can kind of just spread each of them out a little bit, and eventually I'm going to get back to the true distribution. Okay, so these things are going to get close together. But if you sort of assume this, well, then a robustness set that looks like everything near to the empirical distribution in this Wasserstein metric, this is a reasonable uncertainty set because the true distribution should actually belong to it. And then the whole approach with this optimal transport kind of connection to robust optimization is you say, okay, you know what I'm going to do? I'm going to minimize the worst expected loss for all distributions in my family, and I know with a prescribed probability the true distribution belongs to this set, and that's going to certify me a certain level of performance. So this comes guaranteed with a baked-in certificate of performance. That sort of P true belongs to this set is in there. Okay, and so then you kind of have a guarantee that you will generalize no worse than whatever this is. The issue is often this is too conservative, but it does at least come with these guarantees. And there's been some really nice work. Just to real quick give an example. If you have like logistic regression, okay, and you use these Wasserstein transport ideas, it turns out that what you get out is if I measure the cost of transporting x's according to some norm, then I'd actually just get a regularized empirical risk minimization problem where my penalty on my parameter theta is in the dual norm. Okay, these are completely equivalent. So actually this whole idea actually recovers sort of standard regularization ideas that might be familiar from machine learning and statistics. And what's the intuition here? Well, let's just think about, if I look at this objective, you give me one term in this objective, well, what's the worst thing I can do in terms of sort of perturbing my initial data? Well, what I'm going to do is I'm going to find the loss that's the worst, and I'm going to just move the x for that particular loss as far as I can. Just going to take one x and move it as far as I can. My cost of moving x to some x prime, we said, was equal to the norm distance between x and x prime. Sorry. Okay, and so then, and this is going to be very heuristic, but log of minus y x minus x prime transpose theta. Well, when x and x prime are very, very far apart, you know, then I can make e to this. I can basically make this e to the x minus x prime transpose theta, right? And what's log of exponentiation? It's just identity, yeah? And so this is about equal to the absolute value of x minus x prime transpose theta when I make x prime as bad as possible. Okay, and so then the supremum over all x minus x prime, say less than or equal to epsilon of this quantity is just equal to the dual norm of theta times epsilon. Okay, so anytime you have these, and it turns out you can actually do this completely rigorously rather than this vague heuristic that I did, but so you recover standard regularization ideas with these approaches. Okay, I think I'd like to stop here where there are other versions of this, but I want to respect your time a little bit. Let me give a few take-homes here. The perspective that robust optimization offers in terms of kind of generalization ideas is a perspective of certification. You want to have certificates that when you solve a problem, you're not going to do badly in the future. That's what these ideas offer. A lot of the ideas still repose on classical statistical tools. You sort of use some of the convergence ideas there to guarantee that you will kind of be conservative or something like that. The perspectives this offers, and I didn't touch on this very much, it's very different than the robust statistics approaches that are sort of more core statistics, almost converse. And I think Professor Lowe is going to talk about that. Yeah? Yeah. Do you respond to that name? Just curious. You do. OK, that's good. You know, there are a lot of concerns that we have when we work with these. You know, tractability, are these things actually solvable? Sometimes they're way too conservative for practical use, and so you have to be careful with those things. And there's still a lot of open questions about how you actually define uncertainty sets. Can you actually choose Wasserstein balls that are not like exponentially bad in the dimension and things like this? And I think there are some interesting questions with kind of causal inference. If we think of causality as kind of responses that are independent of like what environment you're doing them in. You know, if I'm in my car, I pull left, pull right on the steering wheel. I turn right whether I'm in Ohio or in Berkeley. And we might call that a causal connection. So it might be related to some kinds of robustness. I change the underlying distribution, nothing changes. That's kind of like causality. But I think these connections are not they're not explored yet. So I think there's a lot of interesting open questions here. Okay, with that, I'm going to call it a day. Bunch of references in the last couple of slides, which I'm happy to share. Thanks so much for your attention, and happy to take more questions.
Maybe let's have one question.
There's the slide where you were talking about trying to find a set that contains the true distribution of type probability.
Yeah.
Non-tractable, and then going into other stuff like Wasserstein,
Yeah.
etc. That's a setting in which somehow you're fitting what looks like a metric model because you have a theta there, right?
Yeah.
You're going to assume nothing about the true distribution.
Right.
So you're going from, something where we're basically more well specified to about assuming that we're as misspecified as possible.
Yes.
I'm wondering if there's something in the middle that makes it more tractable. If I could formulate a version of the problem in which I'm willing to assume that it's misspecified but not arbitrarily.
I'm sure there are. I think this is one of the big open questions because, saying, okay, the distribution is just a distribution on R to the D is not a very strong assumption, right? One thing is, if you think about, say, like a linear model or something like that, right? What perturbations of the underlying distribution are presumably actually going to matter? Only things that change kind of these linear statistics, right? Which is actually really a one-dimensional quantity, not a d-dimensional quantity, right? This is just a linear function of x. And so then, well, maybe there's some version of these, maybe there's some version of these which rather than looking at like all possible ways to move things from here to here only does kind of like linear transformations or something like that. And then you still have some kind of guarantee along these lines. But that's very vague. This is all vague things floating around in my head. I think this is a really good, important question, and I don't know the answers. But probably there's definitely something to do here, or to show it can't be done. One of those two.
Until the next session, I think at 1. Yeah.